Hello everyone, my name is Aaron Standard and I'm the CEO and founder of Petabridge and one of the creators of Akka.net, and I'm here to talk about a brand new feature we added in Akka.net 1.4, which is performance tuning for Akka.Remote. So before Akka.net 1.4, the way Akka.Remote worked was one write to an Akka.Remote connection would result in one flush against the underlying socket that powers that connection. Now each time we would flush that socket, that actually produces a system call, and it would be either on Windows or on Linux, depending on what your operating system was. But that system call is actually quite expensive. In particular, they're expensive because it requires a context switch. Memory is essentially being handed off from the client application down to the operating system. And the operating system is going to go ahead and create a real I/O call, where that data is going to get copied into a system buffer and then flushed out to the network using some sort of network interface device. And so as a result, the performance of Akka.Remote under Akka.net 1.3 and earlier could be unpredictable. So just to kind of visualize what this process looks like, this is the .NET channel pipeline. So we follow best practices with trying to build our sort of network infrastructure. And that usually involves pipelining all of the operations that kind of surround your I/O. So anytime we would hand a serialized message, so Akka.Remote would serialize your actor messages into little byte arrays. We would hand that into .NET's iChannel pipeline, the little construct that it uses for pipelining the socket. And then we would queue up a flush command right behind it. So as a result of that, the message would make its way through the pipeline, would append a little header to it at the very end to kind of tell the other end of the socket how many bytes to expect. This is called message framing. There's a whole blog post on it on the Petabridge website if you want to check that out. But then at the very end, as soon as we finished adding that header to the front of the message, we would go ahead and flush the header and the message out to the socket immediately. So every single logical write to the socket also produced one physical write, which was invoked by that flush operation under the covers. As a result of this, the I/O in Akka.Remote in 1.3 could be rather expensive. So what's changed in Akka.net 1.4? We've introduced a batching system that groups writes together and then flushes them all together in one batch whenever we have 30 total messages that are written, or at least 16K that have been written into the channel, or if neither of those first two events occur, 40 milliseconds pass. This allows us to reduce the number of I/O and system calls, and ultimately all these values can be configured inside your Akka.Remote HOCON. So just to kind of visualize what's going on here, we have our message from before. We have our batching channel handler, which goes and updates some statistics about how much information is sitting inside the channel. We have our little encoder, which appends 4-byte headers again. And then all of this data that we're going to write out to the socket is just retained in memory inside the pipeline while we wait for a flush command to be produced. Let's suppose we have 29 messages that are waiting to be buffered, and all these messages were queued in under 40 milliseconds, because that's kind of the sort of the default timeout that Akka.Remote uses to automatically flush whatever's in the channel. Well, as soon as the 30th message passes through the batcher is going to go ahead and trigger a flush message right behind the actual message we want to write out to the network. As a result of that, we're going to go ahead and group all 30 of these messages and write them out to the network all in one go. And so if you want to go ahead and see the numbers for what the performance looks like with and without this change, both of these numbers were taken on the same sort of development machine running .NET Core 3.1. And we can see on the left, these are the figures that come from sort of a pretty standard, the Akka.Remote performance from Akka.net 1.3 or earlier. And you can see here there's a lot of variation with these numbers on the left. Everything from 69,000 to 141,000 down to 38, 32,000, and then back up to 126,000 again. That variation is largely caused by the amount of time it takes to complete the system calls and the context switching back and forth. In the design on the right, what you'll typically see is during this first round of benchmarking, that number will be much lower. And that's because the actors in this case are both writing under 30 messages, so they're relying on that 40 millisecond timeout to flush everything. But once we get above that, we have many more actors, at least 5, all trying to write 20 messages per round out to the socket as fast as they can. We're able to go ahead and hit that batching threshold rather easily. And you'll see the numbers start to go up and they normalize kind of around 143, 145,000 or so. As a result of using this batching system, we're able to go ahead and reduce the amount of variation in performance. We have a much more consistent set of figures now. But on top of that, we're also able to raise the total average throughput pretty significantly. And so it's possible to go ahead and configure the batching system by this new section we added to the Akka.Remote configuration. And these are what the default values are out of the gate. So the batching system is turned on. The number of max pending writes is set to 30. Max pending bytes is set to 16K. And the flush interval is set to 40 milliseconds. It is possible to try to reduce this flush interval, but you'll very quickly run into a problem if you try to set it too low, such as, let's say, 1 millisecond. And the reason being is that every preemptive operating system, whether it's Linux or Windows or OS X, has a clock resolution that is typically going to be around 20 milliseconds or so. A server-side operating systems might have a more precise clock resolution, depending on how they're configured and what their hardware is. But it's not possible to guarantee execution of code within a window of time that's necessarily shorter than that. What we have on the next slide here are some suggestions for how to go about performance tuning your code. The default settings that Akka.Remote ships with out of the gate right now are very good for high message per second systems. You can try increasing or decreasing the number of messages per second to see how that affects your performance. But for systems that have relatively low numbers of messages per second, where let's say your system is largely idle most of the time, but whenever you do receive a message, you need to be able to respond to it very quickly, it might be best in that use case to go ahead and disable batching altogether. Because the batching system is kind of designed for messages that are doing more frequent, continuous communication from point to point. And then if you have a system that has really large message sizes, you might want to increase the number of max pending bytes to be a larger value. Otherwise, if your messages are, let's say, routinely bigger than 16K out of the box, your performance is going to be identical to what we had in Akka.NET 1.3. We're going to be flushing the message every single time because it's bigger than that max pending bytes value. We have a whole article on this on the Akka.NET website. If you go to getakka.net/articles, remoting, performance, there's a whole guide there on how to performance tune it. So thanks for your time. Really appreciate it. And we look forward to getting all of your great feedback and ideas for making Akka.NET 1.4 even better. Thank you very much.